This is a short presentation on work-energy relations in rigid bodies. Let's first look at some of the fundamental theory behind this concept. The primary formula being used in solving these types of problems is the work-energy equation, which is the total work from the first to second state of a system equal to the change in kinetic energy plus the change in gravitational potential energy plus the elastic potential energy. Now, kinetic energy can be split into translational and rotational motion. Translational kinetic energy is denoted by half the mass times the square differences of the final and initial velocities. Rotational kinetic energy is equivalent to half the mass moment of inertia of the system multiplied by the square differences of the final and initial angular velocities. Gravitational potential energy is equivalent to the mass times gravity times the change in height. Note that the change in height is with reference to the center of mass of a body. Lastly, elastic potential energy is equal to half the spring constant times the square differences of the length from an unstretched position. Now moving on to an example problem. We have a slender rod of mass 1 kg and has a particle of mass 2 kg attached to one end. If the body is released from rest from the position shown, determine its angular velocity as it passes the vertical position. Firstly, draw your free body diagram as always. We can determine the mass moment of inertia of the system immediately with the given data. Moment of inertia for a rod rotating about its center is 1/12 ml squared, but here it isn't rotating about its center but around O. So we have to apply the parallel axis theorem, adding the md squared, d being the distance from the center of mass of the rod to its axis of rotation. And lastly, we add the moment of inertia for the particle, which is just mass times the radius of rotation squared. Substituting in the given data gives us 20.33 kilograms meters squared. Here we apply our work energy equation to the problem. Work equals to the change of kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy. There is no work done on or by the system, so total work is equivalent to 0. There is no translational motion, but there is rotational motion, so we have rotational kinetic energy denoted by half times the moment of inertia times omega 2 squared minus omega 1 squared. We have gravitational potential energy in the rod and particle. There is no elastic potential energy in this problem. And this problem is quite straightforward, so we simply substitute all our variables into the equation. Note that the change in height is negative because the rod and particle have traveled below the initial horizontal datum. In the end, we get omega at the vertical position to be equal to 2.6 radians per second. This is clockwise, which is determined just by looking at the diagram. In summary, to solve work energy equations, you first want to draw a free body diagram, then determine if work has been done on or by the system. If not, work is equal to 0. But if there is work, we want to determine the work from the external forces times its displacement and the external moments times its angular displacement. Thank you for watching.